Now, the last video is going to be about the worm gear. So we shall start with the brief introduction to the worm gear, and then we're going to go to the worm gear design procedure. So the worm gears are used to transmit the motion and the power between the two non-intersecting shafts, as you can see in this image. Usually, again, to be with 90-degree to each other. Have threads rather than having the teeth like the most of the gears we discussed earlier, and they can achieve a higher speed reduction but lower mechanical efficiency than the bevel gears. We said the bevel gears can go up to 98%, and this one is going to be around 90%. So again, brief uh, specification of the worm gears about the advantage and disadvantage: a larger speed ratio, silent and smooth operation, small drive size, better load distribution, and self-locking action is possible. Disadvantage is low efficiency, expensive anti-friction materials, and also considerable sliding speed are possible, and considerable heat generated due to high friction. So in this image, we can see the worm contact with the worm gear, showing a multiple teeth contact at the same time, and that's actually going to cause the mechanical contact and the high friction load that cause the heating. So the forces acting on the worm gear, as you can see in this diagram, on the side view, showing the forces acting on the worm gear and the worm itself. And we have a three-dimensional view of the worm showing the worm forces. So once again, we're going to have the tangential, we're going to have the radial, and we're going to have the axial force to be shown. In the next steps, we're going to have more discussion about the calculation of these forces. The worm gear parameters are not much different from the other types of the gears, the worm gear, actually, sorry. So you can see that we're going to have a length, we're going to have the face of the worm is going to be actually depend on the length of the worm we're going to have on it. Same thing, we're going to have outer diameter, we're going to have the radius diameter here. And for the gear is going to be as normal gear, we're going to have the addendum, and we're going to have the center distance to be calculated between the centers of the worm and the gear itself. And this can be mainly a spur gear. Sometimes it's going to be also to use the helical gears for the gear itself, but for the worm, it's just a worm shape cutting. So the worm gear features are: we have the lead angle lambda, we have the Bichline speeds. We can have it for the worm and for the worm gear to be a different equation depending on the RPM value and for the diameters. The velocity ratio is going to be the speed of the worm divided by the speed of the gear. Other geometric properties are going to be similar to the previous types of the gear that we covered earlier in this session. Again, the forces we have on the worm and the worm gear are the three orthogonal forces similar to the helical and the bevel gears. And due to 90-degree orientation, we can find the relation between them is going to be based on the following. The tangential on the gear is going to be equal to the x on the worm. The x on the gear is going to be equal to tangential of the worm, because we said they have 90-degree orientation between them. The radial force are going to be the same for both. Again, to compute the forces, we need to find first what will be the torque, and the torque can be, of course, found from the power. So for tangential force on the gear is going to be 2 multiplied by the torque divided by the diameter of the gear. The x for the gear is going to be the tangential of the gear multiplied by the relation between the cosine of the phi and the lambda. And the coefficient of friction is going to be also involved because of the higher contact surface that we discussed earlier. The same thing for the radial for the gear is going to be a relation between tangential and the pressure angle and the lambda and the coefficient of friction. The T is the output torque, the dg is the pitch diameter for the worm gear, the lambda is lead angle, And usually it's going the phi it's not mentioned, it's not shown here. The phi n is normal pressure angle, and the mu is the coefficient of friction. So due to the higher contact area, the friction will play a major part in the operation of the worm gear set, where the coefficient of friction in mu can be calculated depend on the value for the velocity. So the frictional force can be calculated based on the coefficient of friction, and the static condition, where the velocity is going to be equal to zero, the coefficient of friction is going to be as high as 0.15. As we are going to start to do the operation, the value for the higher speed will result in a higher coefficient of friction, as we can find from the two equations for the low speed, less than 10 feet per minute, or for the higher speed, for more than 10 feet per minute. So these two equations can be used to sketch the figure 1025 about the coefficient of friction versus the sliding velocity for the steel worm and the bronze worm gear. So you can see that we are going to increase the velocity, the coefficient of friction will start to drop. So the power loss due to the friction, or the PL, in the SI unit is going to be equal to the frictional force multiplied by the speed divided by 60. Where PL is going to be in horsepower, and the V is meter per second, and WF is going to be in kilonewton. The input power in that case is going to be equal to the operational power plus the loss power. The efficiency is going to be equal to the PO, which is going to be the output power, divided by the input power. So we start with calculating the service durability, which is a rated tangential load, WTR. And once again, it's going to be using multiple factors like the material factor. Different material is going to have a different material factor, of course. The DG, which is pitch diameter of the worm gear in inches, to be calculated, to be used actually, and the FE, which is the effective face width in inches, and the CM is going to be the ratio correction factor. And finally, we have the velocity factor, CV. So you can refer to the example problem 10.8 in the book, and it's going to give you some idea about how we are going to use this equation to find the rated tangential load. So the values for the different factors that we are going to use in the calculation can be obtained from charts such as the one we have below, which is the figure 1027, which can help us to find the CS, which is the material factor. So you can see that we have three lines has been sketched on the graph, different colors. The green one is the sand casted gears, the red one is the static chill casts or the forged gears, and finally we have the centrifugal casted one. So by identify what will be the diameter of the mean gear diameter, and we can search for that on the x-axis. We can find it in inches or millimeters. Then we intersect the line with any of the material or the material or the method of manufacturing, and then by having the intersection, we can move a line to the y-axis to find what will be the material factor CS. So again, the worm gear design required to have some data to be collected first, like the power to be transmitted and the type of the driver and driven loads, the speed of the driving gear, the center distance, the speed of the driving gear and the velocity ratio, and finally other information related to the problem specifications like the material and other stuff. The design hypothesis is that the gear teeth should not fall under the static loading or dynamic loading during the normal running conditions. Also, the gear teeth should not have a weird characteristics so that their life is going to be satisfactory. Also, the use of the space and the material should be economical, and the alignment of the gears and the deflection of the shaft must be considered, and finally, the lubrication of the gears must be satisfactory. So the procedure will be once again summarized as steps. The step number one, after specifying the design data like transmitted power, the input-output speed, the center distance, the type of the driver and driven load, we can simply find the following. First, we need to specify the number of the threads for the worm or the NW. And this can be anything between 2 to 8 or more. We can specify the diametral pitch value to BD, which we have standards for that, 3, 4, 5, 6, up to 48. And then specify the pressure angle, which can be as a standard 40 and a half, 20, 25, and 30. We need to compute the nominal velocity ratio, which is the RPM of the worm divided by the RPM of the gear, or the number of the teeth of the gear divided by the number of the worm threads. After finding the VR, we go to next step, which is compute the circular pitch for the gear. It's going to be equal to the pi divided by the PD, which is going to be equal to the axial pitch for the worm. The number of the circular pitch value is going to be usually equal to the P, which is the circular pitch of the gear, multiplied by the cosine of the lambda, and the face width of the gear is going to be usually equal to 2 multiplied by the pitch value. Then compute the lead, which is going to be equal to the number of the thread of the worm multiplied by the px, or the pitch value on the x direction. Compute the pitch diameter of the worm within, which can be used, the equation here for the dw, and this will depend on the c value, and simply we can find the number, and then we can change this number by applying at different iterations. Calculating all the lambda is very important. I mean the lead angle, and this can be once again using the equation of the lambda is equal to tangent inverse of the lead divided by the pi multiplied by the diameter of the worm. Remember that once again the value we're going to use in this equation, I mean the tangent inverse is going to be for a radian, not for degree. Now we can compute the pitch diameter of the gear. We can compute the pitch line speed for the worm and the gear, and finally compute the sliding velocity. We can find the coefficient of friction from the figure 1025, sorry, as we discussed earlier. Now, by knowing the power, we can calculate the output torque. The Xg and WRG can be found by using the following two equations that we discussed earlier, after we know the tangential force and the radial force for the gear. The friction force can be calculated by knowing what will be the radial force for the gear and using the tangential force of the gear and the coefficient of friction and the lambda value. The power loss, as we mentioned earlier, is going to be equal to the work loss and multiplied by the speed divided by 33,000. The input power loss is going to be the power loss plus the power output. The efficiency is the output divided by the input, as we have for any efficiency equation. Now, step 3 is analyzing of the gear tooth failure mode. As we mentioned earlier, we're going to have both the root and we're going to have the surface. Usually the root is going to have the bending as a failure, and for the surface, going to have the pitting or the scoring. So for the bending stress, again, it's going to be the same equation that we explained in the case of the other two types of the gears. The stress is going to be equal to WD divided by the YF of the gear, the face width of the gear, multiplied by the PM. And this should be less than the allowable bending stress. Now for the surface durability related to tangential load also can be calculated by using the equation given to us here. We need to find the values for the factors Y, KV, CS, CM, and the CV, as we're going to introduce in the following steps. So we start by finding the factor Y, which is, we know it as the Lewis form factor for the worm gear teeth. As you can see, it's going to depend on the value for the phi n, or the nominal pressure angle. So for the 40 and half is going to be 1, for the 20 degrees is going to be 0.125, sorry, 0.125, 25 is going to be 0.15, and for 30 degrees is going to be 0.175. Now we can simply compute the dynamic load factor Kv by knowing what will be the velocity of the gear, and we can use the equation here, 1200 divided by 1200 plus the VTG. And we can compute the dynamic factor WD by using the WTG divided by the KV value that we found earlier. So we already discussed the figure 1027 for finding the material factor CS. Depending on the manufacturing method we have here, this is for the standard 6034B92 material. Okay, and simply again, we can use the sand casting approach for the DG to be more than 0.125 inches or the 63.5 millimeters. We can have the equation that's given to us here. And if it's going to be less than 2.5 inches, simply we can use the standard value for the CS to be 1000 if we have the sand casting bronzes. For the static chill cast or the forged bronze, again, if we're going to have the DG value more than 8 inches, we can use the equation. Or if we're going to have it less than 8 inches, we can use the standard value of 1000. For centrifugally cast bronze, again, if the DG is going to be more than 25 inches, we can use the equation. If it's going to be less than 25 inches, we can use the standard of 1000. If a standard addendum gears are going to be used, then the DM should be equal to the DG directly, so you don't have to worry about that point. Now, for the step number 6, we can compute the effective phase width in inches. So if the phase width for the gear is going to be less than 0.667 for the diameter of the worm, then the effective phase width is going to be equal to the effective phase width of the gear. Else, if the FG is more than the 0.667 diameter of the worm, then simply the effective phase width is going to be equal to 0.67 multiplied by diameter of the worm. So we can now specify the ratio correction factor, CM, from the figure 1028. You can see that we are going to have 3 zones here. The zones mainly going to depend on the gear ratio or the MG. So you can find the MG, and then simply again to be located in different zones. You just do the intersection with the curves, and then you can find the value for the ratio correction factors, which is going to be also possible to be calculated by using the following 3 equations depend on the gear ratio value. So if we're going to have the gear ratio anything between 6 and 20, we're going to use the equation 1. If we're going to have it between 20 and 75, the equation number 2, or we can use the CM value, equation number 3, if we're going to have my gear ratio anything between 75 and 100. Usually, once again, if you would like to have an Excel sheet that will help you, or do MATLAB program, for example, to help you to design the worm gear, it's strongly recommended to use the equations to find the factors rather than the graphs. Now for the velocity factor, or the CV, we can obtain from the figure 1029 the same way. We just classify the area into 3 zones. So we have the zone depend on the sliding velocity. So the zone number 1 is going to be anything between 0 and 750 feet per minute, and which is equal anything between 0 and almost 3.9 meter per second. And we have the zone number 2 and we have the zone number 3. Now again, just locate what the velocity, sliding velocity you're going to use, then intersect it with the curve here, and you're going to find the value for the velocity factor. Again, if you would like to make your own code or your Excel sheet, then it's recommended to use the 3 equations that we have listed here. Now, the step number 8 is going to be check if the selected dimensions satisfy the following design conditions. The first condition is going to be that the stress is going to be less than the allowable stress. And 117 megapascal for the manganese gear bronze, 165.5 megapascal for the phosphor gear bronze, and for the cast iron, it's approximately going to be equal to 0.35 multiplied by the ultimate stress. The second condition is that the WTR is more than the WTG. The third condition we have is that the maximum deflection worm should be less than 0.005 px up to power 0.5. If these three conditions are going to be satisfied, then our design is acceptable. If not, just do another iteration, change all the selected parameters until you're going to have the three conditions to be satisfied. So that's it for the gear design. Again, we can have a look for an example that's available in the book for the design of the worm gear, but we actually didn't include it in the tutorial session for this week.